Hey guys, so in this video we're going to be going through the quick mechanisms of NABH4 LiAOH4 reductions. Now, I don't think you don't need to know the PCC and the Jones mechanisms because they're a little bit too long, and I've never seen it tested before, so you guys are fine in terms of that. But again, if the TAs may say something different, definitely go with what they're saying. So again, like I said, we're going to be going through the reduction mechanisms, and so the mechanisms are fairly short and they follow a certain logic to them. Okay, so I'm going to try to make it as easy to understand as possible. So first, let's go through the NABH4 mechanism. Now remember, NABH4 can only do ketones and aldehydes, and regardless of which one you use, the mechanism is actually the same. So we only need to show one. They don't work on esters and carboxylic acids, remember. So I'm going to react it. Let's zoom in actually. So I'm going to react it with this ketone. Okay, and so remember NaBH4, right? When we put NaBH4, the sodium separates, and we're going to get Na plus. And BH4, what that actually looks like is a boron to 4 hydrogens. The boron has a negative, okay? And so I'm going to color code one of the hydrogens. So remember you guys learned that H minus is a base, right? If I had H minus by itself. So it also can act as a nucleophile to certain carbonyl compounds, right? But the main important thing is it's that we have it attached to the boron, not a free H minus. Okay, and so rather than act as a base, it's going to actually attack the carbon of the carbonyl, which, if you remember, it's electrophilic. If we look at the resonance structures, now I'm going to show this to you because I want to make sure that you keep resonance still fresh in your heads, because you're not too far away from the final, and resonance cannot be something that you're forgetting because you'll be using it throughout until you're done with Worgo 2. So if we resonate, we're going to be getting this. So you can see that oxygen is a negative, carbon is a positive, right? And also because oxygen is more electronegative than carbon, we can write the structure with partial charges, plus on that carbon, negative there. So remember, a partial positive is more electrophilic, which is why the carbonyl compound, carbonyl carbon is considered an electrophilic atom. So what's going to happen is the bond right here is going to break. So that means it's going to be H minus taking its electrons with it, attacking that carbonyl, right? That carbon. What that's going to do is that's going to kick this double bond up. So we're going to get this, and here's the new hydrogen that we just put. All right. Now, the thing is, I've seen this mechanism different ways. I've seen it where we kick the double bond up and then another step at the same time, which I just broken it down into 2 steps because that's how you saw it on lecture. Okay, so once we get that carbonyl, that O minus, we now have BH3. Okay, then what happens is the O minus attacks the boron. Now, like I said, this is what I was talking about when I've seen this mechanism multiple ways. I have seen it where it looks like this. So this would attack the carbon. And then instead of this coming up here, what it does is actually, they immediately showed attacking the boron in 1 step. Now, on the off chance they would ask you for the mechanism, which I highly doubt, they've asked it. They can ask it in other ways than having you draw it. Yeah, I think either can give you credit, but because the top one was shown in lecture, I would just follow that one. Right. So now I don't think I've ever seen this asked straight up, draw the mechanism. But what I have seen is they will show you the overall reaction. Let's say some ketone reacting with NaBH4 in the product, and it'll be a multiple choice, and they'll give you 6 intermediates, and they will ask you which one of these is not an intermediate, which you could only answer if you knew the mechanism. Okay, so it's going to attack the boron. We're going to get this O bound to the boron, hydrogen, 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 negative on the boron. Then we have some sort of H plus, which remember, because NABH4 happens in H2O, so I'm going to just keep it simple and do H plus. That bond attacks the H, so it breaks off the boron. We get OH with that H. Alright, so that's the mechanism for NABH4. And like I said, if this was an aldehyde instead of a ketone, same exact thing. Now, again, LiAOH4 for aldehydes and ketones, same mechanism. Okay, so don't really stress too hard about that. So you see you can do a couple mechanisms. We know already technically 4 mechanisms. NABH4 for the aldehyde as 1, and the ketone that's 2. Then LiAOH4 for the aldehyde that's 3, and the ketone that's 4. Okay, so very similar. Now remember, LiAOH4 can reduce carboxylic acids, and it can also reduce esters. So there's 2 separate mechanisms for that. All right, so let's start with the ester, because I feel like it may make a little bit more sense. So let's say I give you this O, and then here CH3. That's an example of an ester. Remember, an ester bare functional group is just OR with a carboxylic acid, but instead of an H, it has an R group. Okay, so we have this right here, and now LiAOH4 is going to break up into Li plus and AOH4 minus. So that's going to just look like Al, H, 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 negative. Okay, so I'm going to try to keep it, again, separated as 2 steps. Now, you didn't see this one in lecture, but I just want to keep it as similar as possible. Tax the carbonyl, fix that up. So now what we're going to get, oh, not the minus, sorry, the bond. Yeah, the hydrogen bond. So we're going to get this right here. And again, let's change the color to that. H is red so we can keep track of it. So we got this. Now, remember how here we attacked the boron, right? Now that does not happen here. If you remember the way we just skip ahead to the final product, if I were to have this, and I use LiAOH4, let's have 2H2O, we knew we would get something that looks like this, right? And if you wanted to rewrite it to make it a little neater, we get that. So that whole OCH3 group came off, okay? So remember, so because it came off, we actually need to show that it gets kicked out. So what happens is instead of that O minus attacking the aluminum, it actually comes down. Now this would make 5 bonds on carbon, so something needs to leave. And so the best leaving group right now is OCH3. We're not going to kick out the hydrogen because then we get H minus, and we can't kick out a straight carbon chain. So this is going to leave, giving us this. Okay? And so you see, we're right back at an aldehyde, and we already know the mechanism for this. So again, all we would need to do, take another LiAOH4. I'll just do like this, skip ahead. Negative. And now, let's change the color to blue. Here we have blue. Now again, that comes in. This gets kicked up. Here's the red H. Here's the blue H. O minus. So now it's going to attack the aluminum, and we have the same exact mechanism as up here. We attack the aluminum, we get this weird looking compound, and then it's going to grab an H plus. So our final answer would look like this. I'm not going to finish the rest of the mechanism because it's exactly the same as up top. Right? And so that's drawn with the hydrogen, so if I just didn't draw the hydrogens, we get that, right? Exactly what we thought it was. So that's what it is for esters. Now carboxylic acids are slightly different. Okay, so we have, let's say, some R group over here, some carbon chain, doesn't matter. OH. Let's draw something for the carbon group. So that, OH. Now, we're going to put aluminum, right, the AOH4 minus, and let's color one of these red. Now, carboxylic acid is an acid, right? So the thing is, and now this is going to be a little bit different, the first step is not attacking the carbonyl. The first step, because remember, H minus is also a base, and we have a very acidic hydrogen, H minus is actually going to grab that H and deprotonate carboxylic acid. So now we get this O minus, and that came off as H2. So we have H bound to H, which is just H2 gas, hydrogen gas. So now we have this. Now what happens is another one of these aluminums come in. Now let me just move everything down. So another one of the ALH4 minus comes in, and it's gonna again attack this. This gets kicked up, giving us this structure with an O minus, right? And so it looks a little bit weird. We have like these two O minuses. So like I said, I've seen this mechanism more commonly drawn with the, instead of the carbonyl immediately coming up to give two O minuses, it straight attacks the aluminum in one step. So that arrow showing the carbonyl coming up is usually actually drawn like this. But I'm just going to keep it like this for now. It's fine. Then it's going to attack AlH3. Oh, and here. This is that hydrogen that we just attached. So we get O bound to aluminum, 1 hydrogen, 2 hydrogens, 3 hydrogens, our O minus, and that other hydrogen that we attached. And so what happens now is we have an O minus, right? We've seen here how the O minus came down to kick out the OCH3, right? So this is actually very similar to what's going to happen. This is going to come down, and this is going to get kicked out. So what we get is something like this, and here's that hydrogen we added. Okay? So, and that O with the aluminum and 3 hydrogens gets removed. So now you can see that we're back at an aldehyde. So now, mechanism's exactly the same as up here. Same thing with NABH4 and a ketone and an aldehyde. Okay? So, those are just the mechanisms of how these things work. Again, if you're worried that this may be a little bit too much for you, you can put an index card, and I feel like the chances of it being tested may be pretty low, considering they only showed you NABH4 and not LiAOH4. And like I said, I have seen this tested, but mainly in Orgo 2. But we only had this tested in Orgo 2 last semester in the spring, whereas previous years I've always had this in Orgo 1. Okay? So just be careful, but like I said, make sure you know these. These will be in all your exams. Well, maybe not all exams, but you will need to know this till the end of Orgo 2 because it will always be useful in synthesis. I think I've ended up using Jones or PCC in every single one of my synthesis questions till I finished Orgo 2. Okay? And the NABH4, LiAOH4 stuff, very, very useful. So definitely know these. Put them on your card if you have to, but also understand them, obviously. Right? And so I hope this video helped you guys, and I will see you in the next video.